the last lesson, we were starting to talk about all the application of the theory that I've done so far, and also my other colleagues, so also the S of K, G of R, all the quantities that we have introduced in this lesson, how do they work for water. So in particular, you have heard also my seminar, so today I will talk about all these issues. We started yesterday with the Widom line, and you have seen here in supercritical water how this concept works beautifully, also for experiment, where the lines of isothermal compressibility maxima, coefficient of thermal expansion, and specific heat converge close to the critical point measured experimentally. This is, I remind you, the liquid gas critical point to the Widom line, as foreseen by the theory of critical phenomena. In this funnel, somewhere, there is the line of maximum correlation length, and all these thermodynamic functions, as they get close to the critical point, collapse on this single line. So they can be used as a proxy from the Widom line. Experimentally, you have viscosity, and we have diffusion coefficient, and also dynamics is connected. This was the important take-home message of the lesson of yesterday. In fact, experimentally, we have the viscosity, and instead, we have, from simulation, I calculated the diffusion coefficient, and we see that the change, the crossover in viscosity and the crossover in dynamics, they both converge to the Widom line. And this is because the Widom line is supposed to, what happens is that the Widom line, we are in the one-phase region here, right? But this one-phase region is not all the same. Across the Widom line, when we go left, we have the gas, which is more liquid-like, the supercritical fluid. And on your right, it's more gas-like. So this is the difference. So it's not so strange that also dynamics will understand there is some change in the fluctuation of the liquid from left to right of the Widom line. In fact, in this paper, we sent the important message that the supercritical state is more complicated than when it was thought before, and what is to be studied. In fact, after this paper, there were many others on this issue in supercritical water. Okay. The ST2 potential was the first one used by the seminal paper that I forgot to cite here by Poole, Shortino, Essman, and Stanley. It's a Nature paper in 1992, where they used the ST2 potential to foresee that water has a liquid-liquid critical point. And for the potential ST2, which is an old potential of water, not so used for simulations any longer for the properties of water, but still important for testing, because it satisfies many properties of water for testing the LLCP hypothesis. Rigorously, it was shown in all the following papers that ST2 has a second-order critical point, similar so to the liquid gas, that belongs to the Ising universality class. For those who are experts of critical phenomena, you know that the critical points have universality class. Most of them that we know are Ising. And also the liquid gas is Ising. And also the liquid-liquid with the experiments is Ising. Okay, so I did myself a test for a potential for water. This is a short-range ramp potential, the AGLA potential, that is able to reproduce many characteristics of water, although it's a single sphere. Water is modeled through the interaction. But this AGLA potential has many characteristics of the phase diagram of water, thermodynamic characteristic, and also the second order critical point that matches the Ising universality class. As you can see, we did the finite size scaling, and we did the successive umbrella sampling, and this is these are this is the T raw bell, typical bell of the critical point, and this is the finite size scaling. So these are the several scale. L15 is the length of the box. So as you see, increasing the box, the liquid critical point tends asymptotically to this value, which is the extrapolation of the infinite fluid. You can read this paper for the details. And it is important, here I want to make an important point. Usually, do you remember my seminar when I showed you that we did an estimate in the solution of the location of the critical point through the crossing of isochords plus other indicators that I will show you? Okay, this is an estimate, it's not a rigorous location, and according to someone was not even a rigorous proof. But what we found out for Jagla is that the TC, MC, ROC, TC, and PC, there are mistakes here, are exactly at the same location, estimated with those indicators in this paper done by Limei Su, Sergei Buldivre, Osti Angel, and Jean Stanley in 2006 from molecular dynamics simulation on this very same potential. So this study provides a rigorous proof that is a second critical order, but it also proves that all these methods to estimate the location phenomenologically are completely correct, as the theory predicts, actually, because if you have a crossing of the isochords, you have a critical point. In this case, the critical point is stable. In ST2, the critical point is M metastables, and this proves that liquid-liquid critical points in general can indeed exist in models with competitive structure, because the potential of AGLA is designed in a way that it has two competitive structures. It's done on properties with the double ramp. Okay, so if you design a potential that has competition between two structures, you will have a critical point in which the one-phase reason is a mishmash, and below the one-phase reason, you have the separation of these two structures. Okay? So we saw this already for my presentation. There is some little overlap, but let's make a recap. Let's remember that a normal, because this is more focused on water, and probably during my talk I didn't have time to say too much on that. When you are in a normal liquid, we say that when you undergo a supercooled liquid, generally undergoing a glass transition, passes through supercooled liquid in which the dynamics is mastered by the cages effect. This is a this is a type of structural relaxation, so structural relaxation here. And then when you cross to another regime, which is the one mastered by hopping. And then usually at the melting point, below the melting point, you have the supercooled liquid. Here is the realm of Mach coupling theory. Then you have a crossover temperature, and Mach coupling theory doesn't work any longer a bit, and then the Mach coupling theory follows a bit below the crossover from fragile to strong. So here the dynamics is fragile, here the dynamics is strong. So you have a crossover fragile to strong, and you have an MCT temperature of structural rest, which is slightly below the crossover. But that, of course, at that temperature, the cages are frozen. Hopping started a bit before, but of course, you have the hopping mechanism that starts to dominate the dynamics, and here they dominate it completely. And then you can use the extended MCT to add the hopping, but most of the time people go to the inherent structure analysis that I was telling you about yesterday. And then we have TG, which is the one in which viscosity is 10 to the 13 Poisse, which is an experimental temperature. And it's important to pinpoint the TG of all the several glass formers and make comparisons. And then we have the T0 from the Vogel-Fulker-Kammer and the Kautzmann temperature that may be coincide, but in any case are extrapolated temperatures. You don't get them directly. Okay, so how is for water? In bulk water, Moe coupling theory works. MTC is equal to the singular temperature in which long time ago Austin Angel saw that, and other collaborators saw that isobaric specific heat and other thermodynamics quantity were showing an apparent divergence. But this divergence actually is not a divergence, it's the Widom line. It's a maximum. This is not a divergence, but in the experiment they could see only coming up the, I must have done something terrible. No. In experiment they just saw what happened? Okay. They saw just the coming up, but it's actually the Widom line. And okay. So in these papers here, we show that the bulk water follows MCT, and there was an experimental confirmation by the work of Renato Torre et al., this Nature paper of 2004. Then we found out that in confinement, we still have this crossover temperature, and so we have this paper in Bicor, and this paper in MCM 41, where we found that the Moe coupling theory still works and that we have the fragile to strong crossover. So Moe coupling still works in confinement. We will see some of it. Still works in confinement, as we saw yesterday for the Lennard-Jones binary mixture when confined. And there is this paper by Faraon et al., with a Shaoxin Chen between the authors, PRL, in which they found a fragile to strong crossover in MCM 41, and this J. Fisken letter in which we found it also with the simulation. Okay, so this is SPC, is the potential that we used back in the 1996 when I was at MIT. It's the potential that we did use to prove that water was following the Moe coupling theory. As you see, we have the usual behavior, so we have ballistic, then we have here diffusive, and as we supercool, the liquid starts being trapped in a transient cage of first neighbors that at the end dissolves, restoring the Brownian diffusion. Okay, so this is the diffusion coefficient that we also can fit to the power law and extract the gamma from D. So we found for TC, for the Moe coupling crossover temperature, 198.7 and minus 80 megapascal. And TC coincide if we consider that there is a shift of this potential with respect to the real experimental quantities. If you backshift the phase diagram, we found out already then that TC was coinciding with, was the same as TS, the singular temperature of Angel. But by then we didn't know that it was the Widom line. We just noted this coincidence. Okay. But let's look at the F of Qt. The F of Qt has the typical behavior of the two-step relaxation of glass formers. So Gaussian, plateau, stretched exponential. We fitted, and you can see the fit now that they work very well. We fitted this function with the 1 minus AQ, where AQ is the Lammos-Bauer factor, the heat of the Patou, and the Gaussian with a fast relaxation time, plus AQ, so it's normalized, because this function, as I told you, is the self and is normalized to 1. AQ, e to the minus t over tau to the beta, and it starts from 1 at t equal to 0. And as you can see, the fit work beautifully, and from this fit we can extract the short relaxation time, the one of the ballistic behavior, associated with the ballistic behavior, the long relaxation time, which is the alpha relaxation time of the glass former, and the behavior of beta. Beta is here. While we supercool, it goes to B, you remember, as I told you. From A of Q, we can extract the radius of the cage, and because it's the expression of the Debye-Waller factor. If you remember, if you studied it in solid-state physics, the Debye-Waller factor is a factor in which intervenes in the phonon the particle that is vibrating, okay, in this harmonic potential. So the rattling of the cage can be thought as a vibration in an harmonic potential. So the Debye-Waller factor has this expression. So we can use it with the Q that we are using. Of course, this Q here that you're seeing now is the peak of the oxygen structure factor. And this and the mean square displacement are calculated for the oxygen that is very close to the center of mass. So you see no signature of rotation in this correlator. If I were to use the hydrogens, you would see extra bumps that are due to the fact that you are also evaluating the rotation in the correlator because the hydrogen rotate, while the oxygen is practically coincident with the center of mass. So this is only translational dynamics. If you want to study the dynamics, the rotation together with the translation, you can calculate this correlator altogether. Hydrogen has also rotation. In fact, we did also another study that here in the 1996, in which we were taking into account the rotation to see how they were coupled to translation to make sure that in neutron scattering experiment you were not measuring rotation instead of translation. Because neutron scattering experiments pinpoints the hydrogen, okay? Because it's the hydrogen was the huge incoherent cross-section. So all that correlators will be the correlators of the hydrogen-hydrogen. But the message is that the rotation don't matter for this analysis. Okay, so we found that tau short of 0.15 picosecond, typical, a RC of 0.5 angstrom, which means that the water is trapped from the first, by the first neighbors, which are the usual one that you expect, that basic pentamer that you saw when I showed you the high density or the low density. From tau, we get gamma of 2.7. Let me remind you that from D, we get gamma of 2.73. According to Hammond coupling prediction, this value should be the same, and in fact, they are the same. Okay. Oh, sorry, I put the hydrogen here. In this 1997 paper, you see hydrogens. You have these bumps here, and these bumps here are the libration of the hydrogen. But this libration, are very high frequencies. So very low, sorry, yes, at a very high frequency, so low times. So you see what happens is only that the Gaussian behavior of the center of mass is a bit spoiled by this bumpy region. Apart from that, we saw that search exponential is very similar. So we study what in quantum mechanics is called the connected correlation function. The connected correlation function and the difference with respect to the hypothesis of the factorization gave us an answer. The analysis would be too long for here, but if you're interested, we can discuss it, that rotations and translation are coupled for water only until water is in the cage. As soon as the cage relaxes, they decouple, and so it's only translation for us that matters. That was the answer. And we have actually these two papers. There's one also in 1999. Okay. We saw that we calculated the tau, can read tau here, versus Q as a function of Q. And this was to show just that in the experiment they calculated the alpha width, alpha maximum, supposing that is a Gaussian, but since it is not, because it's a stretched exponential, you have to make this correction. So we wanted to show that you have to be very careful with the experiment. You have to fit to Cole or Cole-Davidson to the Fourier transform of the stretched exponential, because otherwise you get the wrong result. So water in confinement, let me talk about Mach coupling. This is dynamics, how it works in confinement, because I anticipated you that the dynamics works also in confinement. So let me anticipate you that, let me show you just that, that it works also Mach coupling, but you have to know the system. So for example, for these two systems that I will show you that are Vicor and MCM41, are silica glasses made of ports. In Vicor, the ports are 50 angstrom. In MCM41, the ports have 20 angstrom of diameters. In these ports, you need to make a special analysis that I will show you. So in general, when you have a confined medium or water bound to surface of protein or confinement in a space, you have to understand system by system what is the role of confinement and how does the substrate or the confining region modify the properties of water, if there is a modification in the hydrogen bond network, if static and dynamical properties change, if thermodynamics changes. So long ago, we studied with the Mauro Rovere and Eckhard Spohr the dynamics of water in a silica pore, which is a cubic glass of CO2 with the ports that have a diameter of 40, not 50, 40 angstrom. And this is how it happens, how it is in reality, is a maze of ports. But remember when I told you that we have to decide what time scale we want to look at? For the time scale we are studying with molecular dynamics, we don't care about water going to other ports. For that time scale, my analysis is only for water in port. Water has no time to go out of the ports. So we modeled very well the pore, and with the periodic boundary condition, we put SPC water inside. This is the density profile that we got. So these are we did the several iterations of the pore. This is the surface, and as you can see, this is the density profile. We have a couple of layers, bumpy layers, and then this is raw over raw bulk. It goes to a constant density, slightly lower because of steric reason, slightly lower than the water density, but constant. Of course, when you decrease the number of water inside the pore, the hydration level, there is modification in this density profile. And then we calculated then the intermediate stackering function, and we got an unpleasant surprise because we couldn't fit it with the Rausch-William-Watts, with the stretched exponential. It was impossible. As you can see, we have this tail here that it decays very, very slowly. So we were a bit at the beginning worried about that. Oh, this bump here is the famous boson peak, but we will come back to it to show you the difference between finite size in longer and larger simulation, where you can see better the difference between the finite size and the boson peak that both appear in f of qt. But not now. But just to tell you that when you start seeing this bump, is the boson peak. Okay, but then you see we have problem in fitting by the Rausch-William-Watts. Now you have, of course, to know the chemistry and the physics of the system. These surfaces here are highly hydrophilic, okay? The silica surfaces, which we also hydrogenated, by the way, like in experiment. We carved the system, and then we saturated with hydrogen the dangling bonds. It's exactly as they do in the experiment. In experiment, they produced the Vicor, and then they hydrogenated the inside in order to to make the surface less reactive. And so we did the same. We cut at the hole inside the silica, and then we put the hydrogen on the dangling bonds, okay? But in spite of that, of course, the surface is strongly, very strongly hydrophilic. So we decided to make a separate analysis. We calculated the correlator for bound water, so for this first two layers, and the correlator for what we call the free water, so the water which is in the inner part of the pore. So we tried to see whether we could fit with a single stretched exponential this free water. We saw that this water here is very, very slow, while this one was much faster. And in fact, the outer layer water is practically already a glass. The water in contact with the Vicor, the first two layers, this water here is, as you see, completely slowed down. This is the total correlator. And this is finally the correlator. This is the ambient temperature, the correlator of the free water. And as you can see, the dashed part is the fit. As you can see, the fit works to the stretched Gaussian, and the stretched exponential works perfectly. So we started to analyze the free water upon supercooling. Here it comes. And, and as you can see, the fit works perfectly, apart here from the fact that, as we expect here, we have the boson peak feature that produces deviation, but since we don't want to take into account the boson peak here, we just don't care. We need tau, so tau is good fit here, good fit here, we are done. So upon supercooling, we could do the analysis then. This paper were published in the year 2000, so long, long ago, but we found the Debye-Waller factor, the Core-Rausch exponent, which is this beta, the tau, which is the alpha relaxation or long relaxation, and the short relaxation. So we could see how they behave, and they follow perfectly Mach coupling. We did the analysis X, Y, and Z, but it's because of the boundary condition, but we don't care for the sake of this seminar about these slight differences. So we got values that showed us that Mach coupling keep on working. This is the mean square displacement of the free water. You are only seeing the free water now. And as you can see, it behaves exactly similar to the bulk. It also has a gamma that can be extracted. And the gamma is compatible with the one that we got from tau. As you can see here, we have also free water upon supercooling at different free water of supercooling for a lower level of hydration. As you see here, it's very strong, the boson peak. We have a lower level of hydration, but still the stretched exponential function works also for the lower level of hydration. So we have gamma that is increasing, Tc is decreasing when we have a lower level of hydration, but still we get the Mach coupling results. For the full hydration, these are the results of the glassy behavior of the bulk. And as you can see, they are very similar to the free water in Vicor. So inside the Vicor, we have a Mach coupling theory that works. Now I want to show you, this is bulk now, I think. Yes. Now the same analysis works for MCM41, and in MCM41, which is a smaller pore, we also found the fragile to strong crossover. But let's see, I think I put it here later on. But now what I want to talk to you about, show you again, is the behavior of water, because you saw that yesterday in the Lennard-Jones binary mixture, how we see the hopping in water. So we will see now bulk T4P 2005 for several, sorry that this rho is here, for several rho and several t, and on T4T 2005, we will see how it has smoke coupling, also T4T 2005, how it shows a fragile to strong crossover, and then we will see also that it has the hopping below the crossover. So these are the several densities that we studied, and self-intermediate scattering function, we calculated it for oxygen with the usual formula that we talked about in the preceding lesson. And then we fitted the function, the correlator, with the usual form, which is a Gaussian plus a stretched exponential. Oh, here density anomaly, here two things, density anomaly and boson peak together. Okay, so when we change density in water, you see that the lowest density is slower, which is awkward, because usually in a fluid, when you increase the density, it goes slower. I told you that smoke coupling foresees the density and temperature are the same. You can either increase the density or decrease the temperature, and you will undergo the glass transition in the same way. So you will have the Brouwer law that you can test with the rho minus rho c, or T minus Tc. This for a simple liquid, but not for water, because water has this pentamer and this open structure, and the open structure, the low-density water is the mother of ice. It's very slow, it's a very rigid structure, it's a strong structure. In fact, you have a stronger behavior when it's more ordered locally. So, no surprise for water, we knew that already, but let me just underline this to you, that for the lower density, actually water glows slower, because it's disordered, but it's already locally ordered, so it has more stable structures. As you increase the density, it goes faster. Then if you keep on increasing or decreasing, at the end you will restore the normal behavior. But in this region, you see we have this anomaly. So this is the fact that upon decreasing density along isotherms, the diffusion coefficient decreases and correspondingly T increases. Okay, but let's now look at the boson peak. The boson peak is the first bump. These other oscillations are finite size effect, which we have shown, I probably don't have the picture here, by doing the same simulation on different box sides. So we saw those wiggles moving while the boson peak wasn't moving, okay? So this is a real feature, okay? It's not induced by finite signs. These wiggling here are induced by finite signs, because they are not present for the largest box size, while the boson peak is always there, it's not moving, it's a boson peak. What is the boson peak? As I told you, it's our local phonon-like oscillation, but the real reason why there is this onset is still under discussion since I started to work on water. It's 30 years that discussing about this boson peak. So if you want to get into the community discussing, I think it's this, I think it's that, there is an issue here, but I never did that. Okay, so these are the tau values in which we see still the density anomalies, but I don't want to go into many details here. And then with the tau, we found the fragile to strong crossover. And most importantly, the fragile to strong crossover is present upon crossing the Widom line. Look at this value. For the rho 1.03, you will see in a while that we are not crossing the Widom line. You will see it in the phase diagram space. And in fact, the behavior of the liquid down where we can follow it with the equilibration of molecular dynamics is not having the fragile to strong, because it's not crossing the region in which water starts to behave differently. Remember, when you cross the Widom line, from one side you are more HDL-like, the other side is more LDL-like. If you don't cross the Widom line with the isochore, then you always have the same liquid. So you have a slowdown, but you have no crossover in behavior, in dynamic behavior. Okay. These are the fitting parameter of MCT and Arrhenius. So for the first time, I show you the typical activation energy for water. These are the TC for the different density, and the gamma, and they change, of course, with the density. And these are the activation energy. And this is the temperature. So this is the Moe coupling crossover temperature, and this is the fragile to strong transition temperature, which, as I told you, happens a bit before the Moe coupling crossover. The Moe coupling crossover temperature is the temperature in which the cages are frozen. You have this before because hopping starts before the cages are frozen. This is still fit, so I'm in another T minus TC versus 1 over tau, so that you can see that there are clear deviation from the power law. And this is the von Schweidler test that we did. So you remember you have this universal behavior T over tau, and you can see beautiful curves here that are, from that we found the B, H of Q, and this is what I told you I would have shown you. So this is the fragile to strong crossover that we measured in the curves of tau that I already showed you. This is the liquid-liquid critical point for TIP for P2005 that was found phenomenologically by Carlos Vega and José Luis Abascal and collaborators, but then also rigorously by a science paper of 2020 that I quoted during my seminar, which is De Benedetti, Shortino, Zerze. You will see, I think, it again on this seminar, but you have it on the other anyway. So you see, we have done this isochore, and we find these fragile to strong points. So proxy for a Widom line that is pointing, as you see, to the liquid-liquid critical point. Then we did this, and we found no fragile crossover, but as you see, this one doesn't cross the Widom line, okay? This is the phase diagram that we found for bulk TIP for P2005 water. This is the temperature of maximum density line. This is the bulk this is TIP for P2005. This is the experiment, and this is TIP for P, because we had calculated in the past TIP for P, and this is the Widom line of TIP for P2005, and this is the Widom line of TIP for P. As you see, when you go down between TIP for P and TIP for P2005, there is not this big difference also between the critical point. But in any case, we see that the phenomenology of this potential is similar to the experiment. This is the position where Mishima and Stanley, in a famous Nature paper, supposed the liquid-liquid critical point to be. There are other estimates, but according to me, this one keeps on being the most reasonable place where we can find it. And these are the temperature of maximum density line. This is the temperature of maximum density line of the experiment. As you see, the range of the experiment is limited. But I wanted to put also the experimental point there. Okay, so now to the Vanov, so that we can see what happens also in water. So if some people doubt that we are undergoing at a glass transitional Moe coupling out of this stretched exponential, let's look at the Vanov. So this is the Vanov in this region. As you can see, we have this Gaussian that is getting larger and larger. This is how we calculated the Vanov self-correlation function directly from simulation. So as you can see, it becomes larger and larger, okay? Then this is the cage. We are here at the cage, and as you can see, for several times, the correlation function is always the same, because the particle rattles in the cage. So there is the cage. And this is here, where the particle is relaxing. So from 5 picoseconds onwards, if we calculate the G of RT at larger and larger time, it becomes larger and larger. So we have the perfect phenomenology that we expect for the glass transition. We can also fit the cage. Do you remember the Gaussianity of the G self? So if we do a Gaussian fit, we can get the cage region because the molecule is bound in a three-dimensional circular harmonic potential. Do you remember we already used the Debye-Waller factor or Lambos-Bauer factor for RC, which is the same thing. It's bound on harmonic potential. You can get it also from here, from the self. It's the same thing as the Debye-Waller factor. It's another way of getting it, okay? So this is the angular frequency for the cage region. And as you see, the frequency changes with the frequency changes with as a function of temperature with the density. From the fit, you see that the values of the angular frequency increase at a lower temperature because the cage is becoming more rigid. And this is an extra analysis of the Van Hoff self-correlation function for a rho as a function of t during the still looking at the cage, and then this, and is related to the standard deviation, but let's skip it. This is now the hopping. This is one of self-correlation function that you can see here up to 400 picosecond, for 240, for 220 up to 3 nanoseconds, for 210 up to 8 nanoseconds. Do you see that there is a shoulder here? It's developing a shoulder. This shoulder is related to the hopping. Water is a large molecule, so we don't see this nice bump that we were seeing in the Lennard-Jones binary mixture. We see shoulder, but we see deviation from the expected behavior for the structural relaxation anyway. So this is again it, 10 nanosecond. So that was 0.95. This is 0.98. And look here, so this is for T larger than the crossover temperature. This is for T less than the crossover temperature, but this is for T equal Tc less than the crossover temperature, where you start at Tc seeing explicitly the hopping. And again, you can have some hopping here, but you don't see it very well. But when you arrive to the Mach coupling crossover temperature, the hopping is clear. But you have to go, you see, to very long time, because the particle needs to get the large fluctuation, and it's a probability. So it's not so likely that they can jump. So you have to wait so that the particle has time to jump. Okay, so this is also to show you that, do you remember that I told you that when a particle jumps, it jumps to a free, favorable, energetically favorable place, okay? So this means that if this is my water molecule, this is here, and you have other water molecule here, a water molecule is trapped in the first neighbor cage, trapped. It gets the fluctuation, it has to jump. It jumps on a favorable position. So if there is no neighbor here, for example, it jumps on the first shell of the G of R, or it can jump to the second shell. So it can jump to the first shell or to the second shell of the G of R, of the static structure factor. So if I superpose to the Van Hoff self-correlation function calculated for sometimes the G of R, which is the dashed line, you will see that the shoulders, so the place where the water is hopping, coincide with the peak of the G of R which is a further confirmation that it's a perfect hopping process, okay? It can hop only in favorable places, and the most likely one are the place where the GOR has the peak. Did you understand the concept? Cool. So here it is again for a very long time and a very low temperature. So you have one here, one here, one here, and the others are less visible, but they are there. Still, 0.98 peaks of the structure factor and all the shoulders. And this is still the bumpy GOR and peaks of the structure factor. So, hopping is favored where water is less dense. And this connects to the fact that the fragile to strong transition is found upon crossing the Widom line. When water is less dense, it's more likely that you can have the anomaly. So, so you see here, you have the hopping in this part. This is the Widom line. So the fragile to strong transition. This is the Moe coupling crossover temperature, which has nothing to do with the liquid-liquid critical point. And you see that in this region we have hopping, and this region we have no hopping. Okay, so I was telling you that we did also the analysis of MCM41, in which we did a similar analysis with the Vicor, so with the bound and the free water, but we also went more down in temperature in order to find the fragile to strong transition. MCM41 is the acronym of MCM for mobile crystalline material, is a porous silica with an honeycomb structure ordered this time, but I told you that we are not interested in water going out of the pores. By changing the length of the template molecule, the width of the channel can be controlled. And this is the water inside the MCM41. You see the hydrogenated dangling bonds, the blue points, and the water inside the pore. The pore is very small. It's, do we have the, yeah, pore diameter 15 angstrom. And this is the self-intermediate scattering function. Again, we have to use, we have to separate the bound and free water, bound and free. This time the density is more bumpy, but I wasn't sure it would have worked the same water model that we used for Vicor, but it did. And in fact, we could fit here to the stretched exponential. We have less statistics because the pore is small, and also the simulation is 2010. If I would run it again, I would have more statistic now. And this is the fragile to strong transition that we got so beautifully. And if you're interested in more details, you can look at the JFISCAM letter here, in which we made the analysis of bound water, only of free water. So this is only the free water. And as you can see, we have the fragile to strong transition. This is again, we used in that case the Vogel-Fulker-Tamman just because we were comparing to an experiment in which they were using the Vogel-Fulker-Tamman, but I remember you that the Vogel-Fulker-Tamman is equivalent to the power law of the Moe coupling. It's only that you extract other phenomenological parameters. So it depends if you want to compare to the experiment. And then in the stronger part, we have the typical activation energy. These are the parameters of the transition, and this is the experimental part that found in 2005 and 2004 the same parameters, but they were telling them that it was confined, that they were not true. That's why we ran this simulation to confirm this experiment. And this is the first time when it was seen a fragile to strong transition in this case SPC water in water. Okay, we have a peak of specific heat. So for MCM41, the Widom line would be at 218 plus minus 5 for the full density of the pore. Okay, so I have half an hour, so I think I need to choose what I want to talk to you about, because during the seminar, okay, but the excess of entropy is very slow, it's very fast, so I can do it. Okay, so let me talk about thermodynamics now, connected to dynamics, of course. We did already talk about the configuration and entropy in the past. Now let me introduce the two-body excess entropy and how we found that it is connected to the fragile to strong transition. The excess entropy is the difference between the entropy of the liquid and the entropy of the ideal gas. So it's what exceeds the entropy of the ideal gas. It can be represented in expansion in terms of n-body contribution. And if we assume that the main contribution, this is a strong assumption, comes from the two-body term, then we can calculate the excess entropy from the G of R, okay? So if you want to give an estimate of this excess entropy, you can use the G of R. The referee is going to tell you that you have to use also the other terms, but if you find what you want to find, then you win. Otherwise, you lose. Usually in simulation, with theoretician, we always do this guess. I guess something. If I cannot calculate too much, I calculate simpler. If it comes, I win. If it doesn't come, I lose, and I try to calculate further, okay? But we found that the two-body excess entropy as the fragile to strong, as a crossover at the fragile to strong crossover. It is important to tell you about what it is. It's determined by the configurational space available for the system, and that's why it can be connected to the dynamics of the liquid. In fact, there is a relation between this entropy and the transport properties based on the Rosenfeld scaling. This is a scaling that has an idea behind that the liquid diffusion is determined by the collision and the cage effect, and the relaxation time can be related because of this to the excess of entropy. And if we consider the excess of entropy, we have this relation, 1 to the tau proportional to e to the alpha as excess. And this is what we found. As you can see, if we plot S2 as a function of t, we found a behavior, and then we have a deviation from this behavior, where epsilon is t minus the t of crossover. So if we make the fit to the equation in MCM41, we see a deviation when we have a fragile to strong transition. Okay? So you see the fit to this equation related to diffusion has a deviation when we have hopping. And this is for SPC bulk, and this is for SPC free water in confinement, where we have the same result. Okay. So in the rest of the talk, I would like to talk to you about a line of research that has been going on in my group since a long time. And we have studied, sorry, here, this is a long, old slide. Of course, there is no poster here. We have studied a lot, also recently, but I'm not showing you the results today, aqueous solution of water trehalose. Trehalose is a disaccharide, as I told you already in the seminar, a disaccharide that is often used for cryoprotection. Actually, it's very expensive, so they use glucose, maltose, less expensive disaccharide. We did the trehalose because the trehalose is the most efficient. But as far as applications are concerned, since the other also are good, they use that one. We use trehalose because being the most efficient, it would have been easier to see the effect in molecular dynamic simulations. Okay, it's a cryoprotector. It's more efficient than other disaccharides, and it's used for preservation of foods and organs. For foods, for example, and cosmetics, is used alone. For organs and stem cells is, as I was telling you, used in combination with the dimethyl sulfoxide. I have a recent paper that just came out on Jake and Fis on a mixture in which we also added the dimethyl sulfoxide. The dimethyl sulfoxide is cytotoxic, so they add also some trehalose so they can make it lower the percentage of the MSO. They have a completely different function. The sugar, usually if you have a membrane, do not cross the membrane and stay outside. While dimethyl sulfoxide can cross the membrane, and trehalose avoids extracellular ice formation. Dimethyl sulfoxide avoids intracellular ice formation, because when you have to cool down and preserve, you want to avoid ice formation, because ice is larger than water and tends to damage the tissues and the bio-living and in general. So trehalose has this large use. We studied hydration water, and in hydration, as I told you, when we are looking at the relaxation, the slow relaxation of water close to surfaces, it's most important that you keep in mind that the surface has some peculiar behavior. So the analysis changes from surface to surface. In the case of Vicor, strongly hydrophilic, or MCM41, water was sticking there, was already glassy. We took it off, we used the inner part. In this case, we were focusing on hydration water. So what about hydration water? We found out, as I was telling already in my seminar, that there are two distinct slow relaxation that we found for water in aqueous solution of biomolecules. So as I told you the second day during the seminar, we wanted to see what kind of relaxation we have when pure hydration water is close to the surface of a protein. And then we wanted to see whether there is a change when we add the trehalose. So now you are very familiar with this correlator, as we have been talking about them since 4 lessons today. So I don't have to spend much time to tell you that we have also in this case, we couldn't fit the correlator with a single stretched exponential. Oh, by the way, with Vicor, I tried with 2, but there was no way, because the other water is too slow, it's too separated. There was no way. I had to separate the analysis. Here, we tried to fit with 2 stretched exponential, the slow relaxation. One, it's the alpha, and the other is a super slow relaxation that you have only on hydration water. Bulk water or water far away from the protein doesn't have it. Only the first 2 layers of water, the same first 2 layers that we were cutting away on Vicor. You see, in all my studies on water, I found out this. Water doesn't want to stay with the others. That was the message of my talk. No? So when you have a surface, an external field that's perturbing water, water uses the first 2 layers, usually, no more than that. You will see in literature, also in experiment, that usually estimate 6 angstrom, maximum 8 angstrom from the surface, and then you don't have so strong effect any longer. Of course, you have effect because there is this Coulombic potential, but not so strong. Water is still water far away from the surface. So water in a couple of layers screens away the effect of this external potential, and then starts interacting only with the other waters. So this is what we found out too, but this analysis that I'm going to present now, it's only for hydration water, so for the first 2 layers of water. So this correlator that you're seeing now are bulk water, the blue, then the red is water close to the surface of the lysozyme, so only the red part that looks like the Rolling Stones, the Rolling Stones lips. So you see only the red is the water that we use to calculate the correlator. And the other system that we studied, so bulk, pure water close to lysozyme. Lysozyme is a globular protein, and very small. And then we added the trehalose to see why trehalose was so much cryoprotecting. What was the difference with respect to pure water when to hydration water you add the trehalose? As you can see in this correlator, when we add the trehalose, so the red is the pure hydration water around the lysozyme. The green is the hydration water with trehalose. So you see that the trehalose slows down incredibly hydration water. Let me remind you that this is a logarithmic scale, so it's stretching order of magnitudes. Okay, so we had to fit the stretch exponential with two slow relaxation. One, so you see, we have the fast ballistic part is always there. So it's the first term. Then we have a second term, which is the typical alpha relaxation that we have been studied in liquids. And then we have a third term, which is the long relaxation, which is new for us. I did not present this relaxation so far. It's still a slow relaxation, but it has not the characteristic of the glass former. This is related to the glassy behavior, and we will see later on that it's exactly behaving like Alamo coupling as a glassy behavior, etc. But this one, the long one is associated to the interaction of water with the protein, okay? So, alpha relaxation, so this first tau alpha. This first tau alpha has a fragile to strong transition, and this is with the system without trehalose, and this is the system with trehalose. And surprise, surprise, there is not this much difference between the two. They look very similar. You see, the taus are only slightly higher. The fragile to strong crossover happens only 1 degree above. So we have, as far as the glassy behavior is concerned, it seems that water is not behaving so differently with respect to the bulk, close to the surface of the protein. But we have this important extra relaxation that is slowing down a lot water. By the way, the results for protein alone are similar to experiment on monolayer hydration, and you can see this experimental paper by my former boss, Saushin, in 2006, and Schiro and Kupane and Malamash and others, they worked on that. Let's look at the long relaxation now, and here we see the difference. So the long relaxation has a crossover. We will talk about this crossover, but the crossover is from strong to strong behavior. So the alpha relaxation is related to jump. Long relaxation is related to jumps, okay? No structural relaxation. And lysozyme alone has a long time, but as you see in the range of temperature investigated, they arrive to 10 to the some 5, 6, 10 to the third. But when we had the trehalose, they still have the crossover, but they increase enormously. We arrive to almost 10 to the 6. Okay, enormously. So the cryoprotecting ability of trehalose appears to be related only to this long relaxation. And this crossover is besides tied to a famous crossover that protein have. The protein have this protein dynamical transition. So experimentalists observed that when you hydrate a protein, if it's not hydrated, no, but when you hydrate protein and you calculate the movement of the atoms of the protein, so the Debye-Waller factor, of the atoms of the protein that, of course, do not diffuse, not vibrate because are attached to the protein, you see that if it is hydrated, until a certain temperature, they move not very much. Above a certain temperature, which is a threshold, they start moving a lot. They call this transition in movement of the vibration of the atoms of the protein, they call it a protein dynamical transition. We found out that that crossover of the long relaxation appears exactly on the protein dynamical transition. This is practically the delta R associated square with the Debye-Waller factor that we calculated for our protein. So these are our data. And we see we have that the atoms oscillate a bit until 240 and then start oscillating a lot. Okay. So, but the take-home message is that when we look at the, because I don't have many data here, I had more in the seminar that I didn't finish. So now I have to decide whether switch to the more data. But anyway, let me show you this only. Let me tell you only this. When we add the trehalose, this slowing down is much more of both of them. So trehalose is slowing down these movements of the protein, slowing down a lot. Yes, but what were you calculating? The delta R square? Okay, with the Lennard-Jones. And you find this crossover because, yes, but the Lennard-Jones confined close to a certain, no, bulk Lennard-Jones. So you have a crossover with bulk Lennard-Jones in dynamics. And what did this crossover do? Okay. Stillinger and Weber free energy landscape. Yes, so maybe something similar here, but here what? Yeah. Yes. No, but maybe it's everything, yeah, everything is, it's all the same. Yeah, because it's due to water, but it's also, which is important, related to what you say, because of course water is, and trehalose are changing the potential energy landscape. So this crossover is due to the fact, Gustavo is saying, to the fact that you arrive to the potential energy landscape as a point of maxima, and how do you call this cella, we say, where you, in mathematics, I don't know the English. Yeah, it's saddle points. You have saddle points. When you arrive at that point, below that you have, you have a slower motion. Above the saddle point, you have a faster motion. But the phenomena, of course, are the same, meaning that when you add the trehalose and first water, then trehalose, this changes the total potential energy landscape, and you get for the reason that Gustavo is saying, but you get this because of the adding of water and trehalose that modifies the potential energy landscape. So here, okay, here I think that I showed you, or did I show you in the seminar? Yes, that when we add For example, ions in water, the LDL region is shrinking because ions are more favorably solvated where water is less dense. Let me remind you that this happens also in AGLA. I wanted to use these last 5 minutes just to show you something else that I have done, just for fun. Not us for fun, but you. I'm showing you fast results just to open a bit the perspective. We have done studies on spontaneous inclusion of ice in ice age of NaCl. So we mimicked the phenomenon of the brine rejection I was talking about during my talk, and I wanted to show you the simulation. This is the brine rejection. As you see, there is an ions inclusion, but the ions inclusion is not so big. Inside, you see the brine. The brine means very salty water. And we did a study, very nice. We found a very nice result. Ice, as you can see here, is not, sorry, here I have to start it again. It's not distorted when ions are included, not distorted. And we found out that sodium goes interstitial without distorting very much the ice. And the chlorine goes substitutional to water in the lattice, but it substitutes 2 water molecules. So the lattice is not deformed, but water molecules are missing, and in the middle of the position of these 2 water molecules, you have the chlorine. This is the snapshots of the ice with the chlorine, and we can see, if you count, I mean, of course, now you cannot see, but if you count, you can see that there is 2 water missing, and that the ice is not distorted. While the Na, the sodium goes interstitial in this ice. And then something else that we studied relatively recently, just to give you other possible sorts of inspiration for water, was water in carbon nanotube. We use T4P ice. As you know, when you do it, this is the simulation. When you do it, water tends to crystallize, makes beautiful crystals. It depends on the size of the porous. And we confirmed what happened in experiment. In experiment, they found out that already at boiling point, you could have a glass inside the carbon nanotube, and that's what we confirmed with the T4P 2005. In fact, before our study, they had used only T4P for another more simple potential to study water in carbon nanotubes, but T4P ice is particularly well suited for this. So we found our experiments that are our simulation, that is the blue, compatible with the experiments that are in red, as you can see, while the dotted line are the T4P of a previous paper. So as you can see, the T4P ice works very well inside carbon nanotubes. Let me show you the very nice structure, but this is well known. It was already found for T4P. The very nice structure that water does inside the carbon nanotube. When we have a small, as a function of size of the nanotube, when we have a small one, it's also twisted. It's also like the ice rotates also. And we also observe a new ordering of hydrogen. Very well. So I think it's more or less time, right? Yeah. But let me just go to the conclusion, just to a big recap. So Wiedemann in supercooled and supercritical water exist, and water molecules show a second-order critical point. Water show a Mach coupling behavior upon cooling. The fragile to strong crossover happens on crossing the Wiedemann line in water. There is a connection between hopping phenomena, the fragile to strong crossover, and the Widom line. Crossing the fragile to strong line, a weak hopping peak arises and becomes more evident and sharp at lower temperature, indicated a clear connection between the fragile to strong crossover and hopping. We study only translational diffusion, so no confusion with rotation. At the Moog coupling theory, hopping processes completely dominate. At the Moog coupling theory, TC, hopping processes start to completely dominate the dynamics, and the multiple peaks appeared in the Van Hove self-correlation function, in correspondence of the peak of the G of R of the oxygen-oxygen. Hopping is more favored at lower density, where the system is more structurally ordered and has less mobility. The low-density liquid phase of water is characterized by strong dynamics, and the Widom line separates the fragile regime on the HDL side from the strong regime on the LDL side. We have done a layer analysis of supercooled water confined in silica, MCM41, and also in Vigor. And we found there also MCT water and MCT test works, and fragile to strong crossover works. The two-body excess entropy has the same behavior in dynamics. And also results from hydration water show that we have a fragile to strong transition in the alpha relaxation. MCT works, and the long relaxation is coupled to protein motion, and this seems to be the reason, it appears to be the reason of these cryoprotecting properties of trehalose. We have seen also doped dyes and carbon nanotubes. These are some of the papers that we published, but there are more recent ones, but I didn't have time. Why for that? I don't know. I didn't have time to add the more recent paper, but as I told you, my profile is public on Google Scholar. So if you're interested in the latest paper, just go to Google Scholar and Google me and find them. And this is the last transparency. Unfortunately, I will not be able to be here tomorrow because I had some urgent commitment, so I have to leave tomorrow morning. But it was a big pleasure to organize this school with Marcia and also to teach you to make this course, both things, both the organization and the teaching. So let me thank you for choosing this school. I hope that all the lessons, or mine, but also the one of the others, have been useful for you. The field of water is really a very, very nice field with a lot of things still to be discovered. So maybe you, even if you are not in water, maybe you want to consider switching the field. But in any case, I hope I gave you a wide view on the glassy dynamics, which can help you also to study other glasses and all the beautiful anomalies and peculiarity that our ubiquitous liquid has got. Thank you very much. Thank you. And yes, if you have questions, you can ask me. I will be here for the whole day, of course.